Imagine you are standing on a seemingly endless road, surrounded by sandstorms where every 10 minutes the sand erases all human traces. A place where life does not exist. Yet China decided to burn $1 billion USD just to build a road dubbed, "Once you go in, you never come out." In the middle of this arid South Asia region, Tarim Desert Highway, a 520 kilometers superhighway located at the east-west intersection of the Taklamakan, a land dubbed the fire pan of Asia. No residents, no gas stations, no water sources, amidst the scorching heat and fierce sandstorms. Is China hiding some secret here? How could they build a sustainable highway system on loose desert geology that even American engineers were daunted by? In this video, Massive Minds will take you to the death intersection to discover the technological secrets beneath this white sand. To decode the paradox of this billion-dollar project, we must revisit the year 1993. Why did China not open highways in more crowded and bustling areas, but instead chose this remote desert region? The Tarim Desert Highway is situated in the core area of the Taklamakan Desert, which appears extremely arid and harsh. But in reality, beneath that layer of sand lies a million-dollar treasure, approximately 1/3 of China's oil and gas reserves. It's essential to recognize that in 1993, when the economy began to accelerate, energy demand was a top priority. It served as the springboard for China's multi-billion-dollar manufacturing industry. The road served as a strategic transportation artery, the only way to access and exploit this resource. It provided incredible logistical efficiency, reducing equipment transport times from weeks to less than 7 hours. However, before collecting the first drops of oil, the engineers had to face a practical problem: how to map a surface that is constantly shifting accurately. Unlike highway projects in the US or Europe that cross stable valleys, the surface of the Taklamakan Desert is a living entity with constantly shifting dunes. If construction is based on an old topographical map, after just one wind season, the road could run straight into a sand wall that suddenly rises as high as 20 meters. Error here is not just a number, it is destruction. To solve this problem, engineers use LiDAR, an airborne laser scanning technology. By firing millions of infrared pulses every second, these beams pierce right through the shifting surface sand to hit the solid ground hidden deep below. This allows them to strip away the desert's mask and map the true terrain, pinpointing a rock-solid foundation with 3D precision of just a centimeter or two, even across thousands of square kilometers. However, a static map is not enough to cope with real-time shifts. Engineers deployed a DFOS system, fiber optic sensing, buried along the entire route to act as a sensitive nervous system. Just a small movement of sand is enough to exert pressure on the cable, thereby changing the light scattering characteristics inside the optical fiber. At this point, the AI system will immediately analyze this change to determine the exact location where the dune is encroaching. Thanks to the combination of the divine eye, LiDAR, and the nervous system, DFOS, engineers have for the first time subdued the unpredictability of the terrain, turning mobile dunes into accurate digital coordinates within their control. Once the accurate stratigraphic maps from the LiDAR system were in hand, the road construction work also began. The first challenge was the foundation. With the characteristic terrain of sand and wind, the main problem was the topographic deficiency and the loose nature of the structure. It can be simply imagined that, in essence, digging a foundation here is useless. Unlike beach sand, which has a layer of seawater supporting adhesion, desert sand is a dry, extremely fine aggregate with 40% of its 50% of its structure being air gaps. If you deliberately pour asphalt onto this surface in a traditional way, the weight of heavy trucks will compress that air layer immediately, causing the road surface to collapse and deform after only a few vehicle passes. This is the subsidence nightmare that every road and bridge engineer wants to avoid. Building on shifting dunes is a task most would call a fool's errand. But instead of relying on chemicals or binders, engineers have turned to a hidden force: the power of frequency. This is vibrocompaction, a technique that fundamentally rewrites the ground's internal physics. These aren't your average rollers. They are equipped with high-speed, eccentric shafts that send violent shock waves deep into the desert floor. This intense vibration shatters the friction between sand grains, forcing them to surrender their loose structure and collapse into every hidden air pocket. The transformation is absolute. The entire sand mass shrinks by up to 20% in volume. What's left behind is a foundation as dense as bedrock, an artificial rock ready to shoulder the weight of massive transport convoys without flinching. Despite this, the roadbed still has to face the phenomenon of lateral displacement. Put simply, when a super heavy load bears down, the vertical pressure creates an impulse that pushes the sand particles toward both shoulders of the road. Over time, this loss of material diminishes the foundation's density from within, leading to subsidence and the destruction of the surface structure. In stable lands, people can drive piles dozens of meters deep to find a support point. But in the middle of the Dead Sea Taklamakan, where the sand layer is as deep as a skyscraper, there is no eternal support point. It was at this moment that a genius philosophical solution was proposed. Instead of trying to cling to the bottom of the sand sea, humans would choose to package the strata so the road could float on its own. To realize this philosophy, engineers mobilized a peripheral armor called 3D honeycomb mesh, GoCell. These are not ordinary plastic meshes, but a network of high-strength polymer strips, heat-welded to form millions of continuous hexagonal cells, covering the entire road surface like an endless giant honeycomb. Its principle of operation is a delicate combination of geometry and physics. When the compressed sand layer is filled into these hexagonal cells, each cell acts as a prison, confining the sand particles inside. When the pressure from the truck wheels presses down on a spot, the sand particles instinctively want to push to the sides, but are immediately stopped by the walls of neighboring cells. This impact force is not neutralized but is transmitted and distributed evenly across millions of surrounding cells, creating a technical phenomenon called hoop force. The introduction of this honeycomb structure marked a significant breakthrough, increasing the roadbed's load-bearing capacity by 5 to 10 times compared to conventional sand compaction alone. This process transforms loose, fragmented sand into a unified, highly elastic mass, enabling the entire 500 kilometers route to effectively float upon the sea of sand. Finally, the long-awaited moment arrives. As the first layer of asphalt is laid, the primitive construction is transformed into a glossy black ribbon winding proudly across a golden ocean. However, the reality is far more complex. Beneath this asphalt lies an engineered entity designed to endure some of the most brutal thermal torture on the planet. The sun in the heart of Xinjiang is not a source of life, but a massive furnace. In the summer, as thermal radiation is trapped within the sand valleys, the asphalt's surface temperature can soar to a staggering 80 degrees Celsius. At this extreme threshold, standard oil-based materials soften into a viscous mixture that adheres to truck tires like molten taffy. But the true drama unfolds as time turns. When night falls, the temperature plummets to negative 20 degrees Celsius, causing the asphalt to become as brittle as a thin sheet of glass. This violent cycle of expansion and contraction occurs daily, generating billions of microcracks, silent wounds, capable of destroying the entire billion-dollar project if not addressed immediately. To overcome this thermal curse, scientists equip the road with a technology bordering on science fiction: self-healing microcapsule asphalt. This represents the pinnacle of infrastructure engineering, meeting advanced materials science. The secret to this self-healing pavement lies in billions of ultra-durable polymer microcapsules blended directly into the asphalt mix. When thermal stress or heavy loads cause a crack, pressure ruptures the shells. This releases the liquid bitumen stored inside. The bitumen seeps into the fissures, dissolving and rebonding the old asphalt molecules to stitch the surface back together while the damage is still microscopic. This process maintains the road's integrity and blocks out water, all without the need for manual repairs. This is a revolution in human engineering logic. Rather than searching for a material that is immune to nature, an impossible task, engineers created a structure capable of self-repair. The stroke of genius was turning the desert's greatest enemy, that 80 degrees Celsius heat, into a powerful catalyst. However, despite having a durable skin and a solid skeleton, the road could still be buried alive in just minutes if massive sandstorms strike. Sand walls hundreds of meters high can move at the speed of a racing car. ready to swallow every architectural trace in less than 30 minutes. To confront this destructive power, engineers did not choose to build towering concrete walls, which would quickly be buried and overtaken by sand. Instead, they deployed a tactic symbolic of Eastern wisdom, using softness to subdue fury. They created a great wall of straw, covering a vast area of up to 58 million square meters. This is the straw checkerboard system, a network of dry straw squares driven deep into the sand. Seen from above, they resemble a giant fishing net attempting to restrain the desert monster. The principle is a sophisticated solution to neutralizing wind energy. When sandstorms carrying billions of grains strike, they collide with the edges of the straw cells. This friction immediately reduces the wind speed below its critical velocity, the speed necessary for wind to carry sand away. As a result, the sand loses momentum, falls, and is imprisoned right inside the straw checkerboard squares instead of overflowing onto the road surface. But the pinnacle of engineering does not stop there. The engineers also applied a bold aerodynamic design to the roadbed itself. The entire road foundation is calculated to be 0.5 to 1 meter higher than the surrounding desert surface. This design transforms the road into an obstacle with a special shape. When the wind blows across it, it is compressed between the road surface and the atmosphere, creating a localized acceleration of airflow known as the Venturi effect. This airflow automatically blows away any stray sand grains that have just begun to settle on the surface, keeping the black ribbon always clean without the need for human intervention. This is where strategic thinking truly shines. Instead of fighting a losing battle against the storms, we've learned to work with the laws of aerodynamics to turn the wind into a maintenance tool. The sandstorms are no longer the enemy that buries the road. They've become a natural cleaning crew, automatically sweeping the surface clear and keeping the path open for traffic. More than $500 million was spent not to build a dead road, but to create a living entity that harmonizes perfectly with the harshest ecosystem on Earth. From self-healing microcapsules, elastic honeycomb skeletons, to fragile yet resilient straw shields, all have combined into a technological wonder of the century. The Tarim Desert Highway is not just a path leading to oil treasures underground. It is an epic of will and intellect, proving that even in a place where one enters with no way out, humanity can still create legendary journeys. Overcoming all skepticism regarding a costly and crazy ghost road, the Tarim Desert Highway has transformed into an irreplaceable economic artery, serving as a testament to the immense human power to reshape nature. This feat did not merely unlock access to an oil and gas treasure trove accounting for 1/3 of the nation's total reserves, but also directly reduced arduous equipment transport journeys from several weeks to less than 7 hours. Above all, it has been recognized as the first desert highway on the planet to achieve zero carbon status, where 400 solar-powered pumping stations work in harmony with a belt of 20 million shrubs to create an eternal green corridor in the heart of the Dead Sea. From space, the slender green ribbon cutting through the ocean of golden sand stands as a steely affirmation of humanity's status and will in a new era. The Tarim Desert Highway is not just a dry infrastructure project. It is an epic of engineering's transcendence, where pinnacle technologies such as LiDAR and self-healing asphalt have subdued the harshness of the terrain. It reminds us that the only true limit lies not in the brutality of the climate or the shifting of fierce sands, but in human vision and the desire to conquer. We are not just building a path through a death zone, we are rewriting the destiny of lands once thought forgotten. Which impressed you most? The honeycomb armor or the self-healing microcapsules in this mega project of the century? Share your thoughts in the comments so we can discuss the next engineering feats together. And if you always crave to decode the brilliant minds and unimaginable technologies reshaping the world, hit the subscribe button for Massive Minds today so you don't miss the planet's greatest journeys of conquest.